The transport mechanism that a molecule uses to get across a cell membrane will have an effect on the direction of the drug molecule movement. Sometimes it's facilitated if there is a carrier molecule involved to direct it to one side of the cell membrane, as opposed to passive diffusion, where it's simply the molecules cross back and forth until they're of relatively equal concentration on either side of the membrane. And then also that transport mechanism will have an effect on the rate at which the molecule moves across the cell membranes and between compartments within the body. So a carrier molecule will have a distinct effect on the rate at which a molecule will move across a cell membrane. It basically limits it. It limits it because there's only so many carrier molecules. It's a lot like a toll road where there are cars lined up um, across the highway. And if every single toll booth has a car in it, when you come up to it, it's going to be limited simply because there's only so many toll booths or carrier molecules in our case. And so if it is saturated, that's what it's called when all the toll booths are occupied. There's going to be a maximum speed, and that is called Tmax. It simply limits how fast a molecule can get across because there's only so many carrier molecules. So that happens in facilitated diffusion and active transport, where a carrier molecule is the method of transport. So passive diffusion also has some rate limiting um, factors, and one is the concentration gradient. The greater the difference between the concentration on either side of the membrane, the faster the drugs are going to move across. Now, it's not that they move across the membrane faster, it's just that there are more molecules on one side that can move across to the other side. So it's simply just a matter of numbers that it will appear that it's moving faster across that membrane. Molecule size has an effect on how fast drugs move across membranes in passive diffusion. Generally, think about which you think would be smaller would move across or larger. If you guessed smaller, you're correct. The smaller the molecule size, the easier it is and faster it will move across. Um, and then lipophilic. So I brought this up before. Our membrane is this bilipid phospholipid membrane. And if you remember, lipophilic in passive diffusion, those are the molecules that will move across the membrane because like likes like. So this is composed of fats. If we have a lipophilic drug, it's going to readily move across. If it's hydrophilic, so water loving as opposed to fat loving, generally the way that those molecules move across a membrane is via a carrier molecule. That's how they get across. They can't move across this membrane because this is fat, the hydrophilic is water loving, it just kind of doesn't get to cross over that. Um, and so temperature will also have an effect. This is one of the reasons why we want to warm animals if they are cold. First of all, we want to get their core temperature up so that the body can function well. And part of that functioning is that drugs will move across a membrane in warmer temperatures better than in colder temperatures. And lastly, membrane thickness. This is probably something that is pretty intuitive. If we have a thinner membrane, it's a lot easier for molecules to cross than in a thicker membrane. So let's think about phagocytosis and penocytosis. Would these be fast or slow processes? I'm going to go back up to our diagram of this. This is a pretty involved process. Either one of these is pretty involved for that membrane to basically engulf the particles and bring them into the cell. So as you might imagine, this is not a fast process. This is a fairly slow process. And again, it's not used that often. And so there are not as many molecules, typically they're large proteins brought across this way. All right, so going back to this lipophilic or hydrophilic property of molecules, um, the lipophilic or fat-loving drugs will readily move across membranes if passive diffusion is the way that they get in. And hydrophilic or water-loving drugs tend not to move across these membranes. They tend to move in the fluid if they're placed, let's say, subcutaneously or intramuscularly. They move through the water between the cells to get to capillaries. Drugs generally move very readily into capillaries. There's no boundary. It doesn't matter if they're lipophilic or hydrophilic. Once they reach capillaries, they will be able to enter into them. So lipophilic, they'll move through the membranes. Hydrophilic, they'll move around and between the cells to get to the bloodstream. So these properties also can be defined by the charges, the chemical properties of charges on these molecules. So polarized means a molecule has charges at the end of the molecule, and maybe on both ends. And ionized means that they have a net positive or negative charge. Basically what you need to remember is if it's charged or has charges on the end, it is a hydrophilic molecule. If it is non-ionized, does not have a net charge, or does not have charges on the end, non-polarized, it is lipophilic. It has that particular property to it. So the other thing, we're going to get into this more a little later, but I'm going to introduce this concept that this charge or polarization has, it's a chemical property and it has to do with the environment in which a drug is placed. And the body has a variety of environments, especially when we're talking about the GI tract. We go from a relatively neutral pH in the esophagus and mouth down into the stomach, which has quite an acidic um, property to it. It's on the acid scale. It's probably about 2 or 3 pH. And then when it gets into the intestinal tract, that is more of a neutral pH, around 7, sometimes a little bit alkaline. And I want to stress that in ruminants, the rumen tends to be more on the alkaline scale, so away from acidic. But depending on where a drug is in the body, uh, a drug will either take a hydrophilic form or a lipophilic form. And as it moves from an acidic environment like the stomach, it may change from being lipophilic to hydrophilic. So in that case, if a drug is more lipophilic in the stomach, that's where it's going to be absorbed. If it tends to be more lipophilic in the more neutral environment, and it's simply a property of the drug, more of the drug will be in a lipophilic form, and that is where it will be absorbed. We're not going to have you calculate or consider this a whole lot. It's just something to understand that, especially if drugs move between different membranes and there is a change in pH, it may actually trap the drug in certain places because the drug may become more of the hydrophilic form. So I'm talking about more of um, the way to think about it is that there's a certain percentage of a drug that will be hydrophilic and a certain percentage of a drug that will be lipophilic in some part of the body. So it's not strictly one or the other. And that is, that all of these things have been taken into account when a drug manufacturer is looking at a drug and considers where the drug is going to be absorbed and how it's going to be absorbed. And so some drug uh, tablets will be coated with a form that gets the drug through the acidic environment of the stomach so it can get into the um, neutral environment of the enteric of the intestinal tract, and that may be where it has its lipophilic form and is more readily absorbed. So it's just something to think about, that drugs change their properties depending upon the environment that they are in, and specifically the pH that they are in. They can go between hydrophilic and lipophilic.